Join us on a voyage through the wormhole, your gateway to groundbreaking thinking on AI, space exploration, a healthy planet, and a more intelligent future. I'm your host, Jonathan Knowles.
The Wormhole is produced by Trillium Technologies, leading the application of artificial intelligence for planetary stewardship, space exploration, and human health. Help us explore what's over the event horizon by following us on LinkedIn and Twitter at trillium.tech. Together, let's build an intelligent future.
Thank you for joining us as we explore the domain of heliophysics in this special wormhole interview focused on the phenomena of aurora. And we will definitely be talking about both Borealis and Australis aurora, for those of you who might be wondering. At FDL, we have been engaged in heliophysics research for 8 years, and we're fortunate to hear from some of our amazing faculty and researchers here on the Wormhole who bring such a wealth of knowledge and experience, as well as groundbreaking research that has significantly advanced our understanding of solar phenomena and their impacts on the solar system. NASA has designated 2024 as Heliophysics Big Year. As you might know, the sun has been extremely active, and this year in general, but specifically over the last week. So let's get right into it. And today we are talking with my very good friend and colleague, Dr. Tom Berger. He's the director of the Space Weather Technology Research and Education Center at the University of Colorado Boulder. He is also an FDL faculty member. You might have joined our recent wormhole interview with Tom, where we talked a bit about space weather. We thought it might be kind of interesting to bring Tom back, do this again, but this time focus a little more on aurora. Now, heads up, if in fact we have some technical difficulties here, and we might, Tom is joining us today from Italy. And just before we got started, we noticed there were some network issues he was having. We think we've resolved them. If it turns out to be unresolvable, we will be rescheduling this wormhole with Tom. So let's see if we can make it through. Tom, it's always good to see you. Even though you're not in 1080p resolution, nor am I. I've lowered my resolution as well, just to, I don't want to look too much better than you. But how are you doing, my friend?
Pretty good. I can hear most of what you're saying, Jonathan. Thank you for having me. We can, I think, proceed with the interview. Let's see how the internet cooperates here in Italy.
Very good.
As we progress, we may have to reschedule, given that occasionally the audio starts getting pretty garbled.
Okay, we'll go a little slow here, and I'll make sure that I have plenty of pauses to get the audio through to your end. Let's start here, Tom. If you could please do a little brief introduction, just as a reminder for folks about what space weather is and why it's important for us to study it.
Well, the space weather is generally the subject of everything happening in space around the Earth and all the way back to the sun. And if you want to take it further, it's the interaction of the sun with any of the planets: Earth, Mars, the Moon. It's really the study of the interaction of solar dynamic output with any of the planets. We tend to focus on the Earth here. And certainly last week we had a great show, because there was a lot of new solar activity which was directed in our direction. Sometimes the sun is active, it fires off in the other direction. We don't see anything. This time, a lot of the activity came in our direction, and we got some really good auroral light shows and other effects from this solar activity, this space weather, if you will.
And of course, the sun does go through these solar cycles. On average, about every 11 years, we go solar maximum, solar minimum, solar maximum. We are entering solar maximum As you mentioned, we have had some serious activity. As a matter of fact, here is let me see, there's the sunspot group that has been responsible for these coronal mass ejections. And even this morning, I was receiving other alerts about solar flares. A very exciting time in heliophysics. I think it's fair to say that the source of space weather, of course, is the sun. There are three primary components of what the sun is doing that affect us. If you could, again, very briefly, just as a reminder, remind people about the solar wind, what a solar flare is, and what a coronal mass ejection is.
Sure. So the sun, as we know, is this giant hydrogen bomb in space that's continually churning and creating enormous amounts of energy. And it also has a magnetic field because it's a rotating star with very complex structure. And that magnetic field actually ends up doing some interesting things to the atmosphere of the sun. It heats it to millions of degrees. The normal sort of surface of the hydrogen bomb, if you will, is only say 10,000 degrees or so. But the upper atmosphere of the sun is heated by the magnetic field to millions of degrees. And one of the consequences of this is that the sun's outer atmosphere is continually flowing away from the star in all directions, and we call that the solar wind. So the solar wind is a magnetized plasma. It's not very dense. In fact, it's very underdense, but it's a magnetized plasma that flows throughout the solar system at supersonic speeds, really. So it's flowing off at very fast speeds, 300, 400 kilometers per second. Uh, and this solar wind can vary in intensity just without any sunspots or any other activity to cause activity on the planet. So when this magnetized plasma from the solar wind hits a magnetized planet like the Earth, you get essentially geomagnetic storming, as we call it, where the geomagnetic field is jostled around by this solar wind. So this happens all the time, and occasionally we get sort of what we call minor to sort of serious solar geomagnetic storming just from the interaction with the solar wind. However, the magnetic field of the sun also, as you mentioned, undergoes this 11-year cycle where every 11 years or so it gets a peak of magnetic strength and activity that shows up in the form of sunspots. So the more sunspots that are on the sun, the more magnetically active the sun is. And sunspots in particular are regions where that magnetic field can get really concentrated and start building up energy in the outer atmosphere of the sun. It's kind of like twisting up a rubber band. All the magnetic field lines get twisted and tangled, and energy gets stored in them. And then we have what's called a solar magnetic eruption, where these magnetic field lines finally break suddenly, very impulsively. They release billions of joules of energy in essentially hundreds of millions of hydrogen bomb equivalents of energy in this one eruption. And that eruption then causes what we see as photons coming off the sun, usually mostly in X-rays and ultraviolet, but sometimes even in visible light, we'll see a solar flare, the photons from the eruption. At the same time, this eruption throws out billions of tons of plasma into the solar wind, the background solar wind. So suddenly the solar wind is not just this smooth outflow from the entire star. It's got a giant cloud of extremely high speed ejecta, which we call the coronal mass ejection. And that's what causes the big geomagnetic storming like we saw last week, where the sun last week threw out 6 or 7 CMEs. It had 6 or 7 eruptions in a row, threw out 6 or 7 CMEs in our direction. Some of these piled up in space. And when they actually came and hit the Earth and collided with the Earth's magnetic field, the magnetic plasma in these CMEs really jostled the Earth's magnetic field, creating a very large geomagnetic storm. And that's the root cause of everything we saw last week, a coronal mass ejection colliding with the Earth and causing a geomagnetic storm to occur.
And of course, this can cause a variety of issues for us with regards to some of our spacecraft, things such as communication satellites, GPS. As a matter of fact, I happen to serve on the Advanced Technology Council for John Deere, and with John Deere, an organization that has quite advanced technology, including GPS-powered autonomous farm equipment. They sent an alert out to all of their customers saying, hey, don't rely on GPS during this time because there could be issues with regards to this effect. Radio communications, as a amateur radio operator, I'm very familiar with what these things can do. So it definitely affects and sometimes plays havoc on some of our systems.
Oh yeah, in fact, it's a kind of a double whammy with these big eruptions because the flares that accompany the eruptions can flood the upper atmosphere of the Earth with X-rays and extreme ultraviolet light, which over ionizes the ionosphere, if you will. And suddenly, radio communications become garbled. GPS signals have trouble penetrating to the ground because the ionosphere becomes unstable and it scintillates, as we say. So you suddenly start seeing GPS signal unreliability. And then when the geomagnetic storm hits, that causes yet more heating of the upper atmosphere of the Earth, so much so that it actually expands the upper atmosphere of the Earth into low Earth orbit, where low Earth orbit satellites begin to feel much more drag and instability, aerodynamic instability, flying in space. Um, Regarding the GPS issues that we saw with this storm, I did hear from John Deere representatives that it became inaccurate during the peak of the geomagnetic storming to the order of a few meters. And so there were tractors out at the time plowing new fields, and they were meters off of where they should be. Now, this is a problem because although they still went straight and they still plowed these fields, apparently just fine. What's going to happen is when they come back to harvest on these fields, the tractors are going to be 3 or 4 meters off of where they should be if they use GPS during the non-storm period, because they won't match. The GPS will not match what they experienced during the geomagnetic storm. So I heard they've sent out an advisory to farmers saying if you plow during the storm, be ready for the coordinates to be wrong when you go to harvest these crops. So we're going to have effects of that kind of magnitude throughout this growing season.
It's fascinating to consider that our food supply is so closely tied to these geomagnetic storms and so many other things.
Yeah,
Point of sale transaction systems and global markets at the various stock exchanges depend on GPS and so many other things, in addition to, as we said, our communication systems. So it is important for us when we think about the answer to why is it important to study this. This is one of the reasons why it's important to study this. The impacts can be
absolutely.
significant. So we did want to get right into the aurora today. Let's shift to that right now. What exactly is it that is happening when we see the aurora? First of all, it happens, it's often happening at our north and south poles. We had something
Mhm.
special happen, but what is it that is actually happening that causes
So
the
the
aurora?
aurora, the basic cause of the aurora is energetic particles, mostly electrons, coming in along the magnetic field lines of the Earth into and then because the magnetic field lines converge at the poles, typically most of those particles are funneled into that polar region where they collide with oxygen and nitrogen molecules and atoms in the upper atmosphere, which then glow like a neon light. So it's essentially an electrically charged neon, well, not a, it's an electrically charged discharge light source occurring in our upper atmosphere. Now, this, as you mentioned, can happen all the time when there's solar wind jostling the magnetic fields, and some of those magnetic fields reconnect. They then dump some of these particles into the polar regions. But when you get a very big CME and a train of CMEs, as we had last week, then you get large scale geomagnetic reconfiguration, if you will. And it turns out that the magnetosphere of the Earth, this bubble around the Earth created by the magnetic field of the Earth, it itself begins to have reconnection events where the magnetic field and the tail of the long drawn out tail of the magnetosphere in the solar wind begins to really be jostled around, reconfigured, and when it reconnects and has these sort of magnetic reconfigurations, it itself accelerates particles and electrons in particular back towards the poles. And that's what we saw last week when you get that sort of strength of reconnection and electron injection into the polar regions, you get a much stronger aurora. And the auroral zone, where these particles come into the atmosphere and cause the glowing of the aurora, expands southward. So suddenly you're seeing the aurora from, as I did, from Boulder, Colorado at 40 degrees latitude, whereas normally you have to be 55, 60, 70 degrees latitude to see the aurora. And it's really, so it's the strength of the geomagnetic storming which determines the size of the auroral zone, if you will, over the poles. And as it gets stronger, it goes farther and farther south. So this particular storm had auroral sightings, I believe, all the way down to Florida in some cases. Now that doesn't mean the aurora is overhead and it's, blindingly bright. It means that you can see it typically over the horizon. For instance, in Boulder, we could see it, but it was in the north horizon region, and it really was pretty dim. You had to have by eye, it was just sort of a dim fog. If you used your camera on your phone, however, it has a much more sensitive detector than your eye, and it could see the green and the pinks and the purple colors from the aurora. But again, pretty far north for us.
And Colorado historically has a very famous story around being able to see aurora from 1859, doesn't it?
Yeah, because in that case, that was a much, much bigger storm than what we experienced last week. And so in that storm, the aurora was so powerful that it came almost overhead in Colorado, in Boulder, Colorado, and it created an enormously bright red diffuse aurora, which was so bright that some people thought there were fires going on. The legend has it that a mining camp was awoken because they thought it was dawn and it was time to go to work. So that was the 1859 Carrington event has many reports of the aurora being sighted much farther south than this storm and overhead, even in places like Boulder, Colorado, and around Denver. So that was, yeah, anytime the bigger the storm, the farther south the aurora goes and the brighter it gets.
And how does the color spectrum of the aurora change with the altitude? And what does this tell us about our atmosphere's composition?
Each color you see in the aurora is due to a specific molecule in the atmosphere. So the dominant color you see in an aurora is green, and that's coming from oxygen atoms, and that's coming from fairly low down in the upper atmosphere anyway. So around 80 to 120 kilometers, these particles, these electrons are penetrating down to those altitudes, colliding with oxygen molecules and causing that characteristic green glow of the aurora. There's also a significant spectral emission from oxygen in the red region of the spectrum, the visible spectrum. And that's typically caused by lower energy electrons that don't penetrate as far down. And therefore, you see the red aurora typically sitting above the green aurora, as we did last week. And sometimes that can appear sort of magenta reddish or pinkish. But that is still oxygen being excited by electrons. But in this case, electrons that are somewhat lower energy, so they don't penetrate as low, and therefore the oxygen atoms can stay sort of in a sort of semi-excited state, if you will, and emit this more rare red glow. And then we have nitrogen emissions, which are sometimes in the purple and even in the blue sometimes. Those are more rare. I didn't see any of these emissions in the storm last week, but some people did report seeing more purplish nitrogen emissions towards the polar regions. This is again due to fairly energetic precipitation colliding with nitrogen molecules and causing a different color. So the color is indicative of which molecule the electron is colliding with, and also what altitude it's colliding with it.
Are there any, well, first of all, do aurora occur on any other planets or moons of those planets?
Yes, they do. In general, wherever you have a magnetic field, which can channel these energetically charged particles down into an atmosphere of any kind, you will see aurora. So we see it very commonly on Jupiter, which has an enormously powerful magnetic field, thousands of times stronger than the Earth. It channels both solar wind electrons and also ions and protons and things from its moon, Io, into its polar regions, creating a very bright, at times, aurora in the polar regions of Jupiter. Saturn also has a strong magnetic field. It has aurora in its polar regions from the solar wind and its magnetosphere interacting with the solar wind. But even Mars has almost no magnetic field. It has a sort of a remnant crustal magnetic field, very patchy and spotty. But in a very large CME collision with Mars, as we saw back in 2012, for instance, they will see sort of a diffuse aurora around these patches of magnetic field. And when I say they, I don't mean Martians. I mean the satellites that are orbiting Mars from NASA right now. But if there are any Martians, they will see a patchy, diffuse aurora where Mars still has a remnant crustal magnetic field.
So not only does our magnetic field allow for these beautiful lights, how important is the magnetic field here on Earth to life on Earth?
Well, that's a really good question, and I think it's still under debate and research. The basic thesis is that the Earth having a fairly strong magnetic field protects us from a lot of the solar energetic particle emissions by funneling it into the polar regions and then having an atmosphere where these particles are stopped, if you will, before they can come to the ground. And if lacking both an oxygen and nitrogen thick atmosphere and a magnetic field, these solar energetic particles would just be streaming straight to the ground where they could potentially, say, cause DNA damage and mutations of life trying to establish itself on a planet. So that's one of the problems with Mars is A, you have a very weak magnetic field, B, you have almost no atmosphere. So solar energetic particles and also cosmic rays, these very energetic protons from the galaxy and other galaxies even, they come straight down to the surface of Mars. And therefore, if life existed on Mars in the past, it may have been because Mars had a much thicker atmosphere and a stronger magnetic field to protect it from these particles. Now that it doesn't, it's very unlikely that life could develop on Mars because it's constantly being bombarded by essentially radioactive emissions from the sun. Although radioactive isn't quite the right word, but essentially it's the same thing. It's energetic protons and electrons and ions constantly bombarding the surface, which would be pretty difficult for life to establish without constantly having its DNA scrambled, if you will. Again, that's sort of a hypothesis. It hasn't been definitively proven, but seems to make sense.
It seems to make sense. I did just read a paper this last week, fairly recent, that talked about the possibility. And by the way, we remind everyone that a paper does not a fact make. This was a paper that I read. People often said a study and draw lots of conclusions. I thought this one was interesting, that due to solar activity about 600 million years ago, the amount of oxygen on Earth was increased. It allowed for other molecules to escape, increasing oxygen. And we see an interesting pattern of very strange looking life during that time that lasted for millions of years. So just another fascinating thing to consider, that we think life probably wouldn't do so well for the reasons you just said, and perhaps even life finds a way to do other things under such circumstances. And when we think about astrobiology and the origins of life, it seems it's important for us to think about the role the sun plays on that as well.
Yeah. I call this the field of stellar planetary interaction physics, and it's a very dynamic and lively field of which space weather here at Earth is a subset, really. So we can study our planet and the interaction with our sun, but there are many other suns out there, very different stars, very different planetary structures and atmospheres, magnetic field combinations. So it's a fascinating field that I think has a long way to go before it's anywhere near being exhausted in terms of these interesting theories of life and how and sort of the mutagenesis, if you will, of life on planets.
Are there any misconceptions around auroras that you are think come to mind?
Yeah, there's of course many misconceptions that are so far afield they're not really worth discussing.
Wait a minute. Wait a minute.
Things.
Are you challenging my notion that auroras are called by Paul Bunyan, the giant lumberjack wrestling with his big blue ox babe, or that Paul invented aurora so he could work, what is it? The legend says 3 10-hour shifts foresting.
Yeah, yeah. I actually heard that on a local newscast the other night. So yes, that does exist. Um, Outside of those rather fanciful interpretations, there's also the idea that the aurora can somehow cause problems on the ground. That it might indicate um, things like energetic particles reaching the ground and perhaps harming you. For instance, as we talked about earlier with DNA damage. This is pretty much impossible. The fact that the aurora is glowing 80 to 100 kilometers over our head means that most, if not 99.9999% of the particles are stopping up there, and there's very little threat of being bombarded by electrons on the ground. Uh, that said, there are quite a few effects that we're still learning and understanding. As we mentioned earlier, GPS is a problem, and it's really a problem when you're underneath an aurora because there, you've got a tremendous disturbance in the ionosphere, and the signals really have a hard time getting received clearly and synced up. And so there's a great saying in Alaska that I love to repeat, which is, "When the aurora is strong, GPS is wrong."
I
So
love
it's
it. I haven't heard that. That's great. And it's
yeah,
fascinating
so
that we, for millennia, have developed so many ideas around the aurora from many cultures around the world. And it's a bit all over the map, just in Alaska, of course, where indigenous people have been for millennia. There are some groups that think it portends bad things, and others that aren't so far away, just in Inuit culture, and their nearby relatives inland a bit who think it's good and it's bringing good things. So we've come up with lots of interesting ideas in northern Scandinavia and parts of northern Scandinavia. One group believed it was caused by foxes brushing their tails on the snow that was causing sparks and causing the aurora. We are creative, we humans, in
yes,
trying to
we are.
explain phenomena, aren't we? Yeah. Well,
Yeah,
besides
it's
all
a
that,
constant quest.
why is it important for us to study aurora? What kind of things do we really learn at the end of the day?
Well, the aurora really tells us, the sort of you can get from the aurora the strength and the flux of the energetic particles into the upper atmosphere, which then we now know is actually altering the chemistry of the upper atmosphere. So as these particles are coming down and creating aurora, they're also doing things like creating strange molecules like nitrogen oxide and nitrous oxide and what we call the NOx, N-O-X, where X could be one, two, three, whatever molecules of oxygen combining with nitrogen in these funny ways. And these molecules can actually damage ozone, for instance. They can react with ozone to destroy ozone. So there are upper atmospheric chemical reactions and further on down sort of secondary, tertiary propagating effects from these chemistry changes we don't quite understand yet. And they may actually be fairly significant in shaping the upper atmosphere's chemistry and therefore its radiative qualities and how hot it is in the thermosphere, which again can impact how much the thermosphere expands into low Earth orbit and causes excess drag on satellites. So there's still, I think, a lot of middle and upper atmosphere chemistry, if you will, that isn't really fully understood, which is intimately associated with auroral electron and proton precipitation into our atmosphere. So that's that to my mind, that's sort of the main kind of frontier of auroral science. I think for the most part, we understand the aurora, how it's formed. As you say, we've pretty much debunked most of the old wives' tales about how
I'm
it's
still
formed.
looking for some evidence about Paul Bunyan, brother.
There's another one where people think you can hear it. That's a very persistent sort of. I don't know if I want to call it a misconception. It's a claim. People say that when there's a strong aurora, they can hear a kind of a hissing sound. Um, I'm not going to say it's not true, but it is something that I think is sort of still out there and interesting.
Fascinating, real fascinating. And of course, our work together and with others on this topic that we're talking about today, heliophysics, is really at the intersection of AI, specifically machine learning,
Mhm.
mostly machine learning, I should say, and heliophysics. Uh, what do you believe are some of the things we might see when we think about the future of the kind of work that we're doing now using this very powerful technology when applied to heliophysics research?
Yeah, I think the physics of geomagnetic storming, the solar planetary interactions we talked about, are so complex that a physics-based model really has trouble capturing all of the detailed physics, which include things like turbulence of the upper atmosphere winds. And uh, I think what AI really is going to hold promise in this field for is developing predictive models that are data-driven. Now the problem is getting enough data, but I think eventually we'll be getting enough data not only on the sun, which we are now collecting, petabytes of image data from say NASA's Solar Dynamics Observatory satellite, but we'll start to accumulate enough data about the auroral zone and the upper atmospheric chemistry I was talking about earlier, and the winds that occur up in the thermosphere and how that can affect atmospheric expansion into Leo, that we'll have, I think, a shot at creating um, machine learning predictive models of these very complex physical reactions when geomagnetic storms occur. And I think it's going to be that, as we're seeing now in the terrestrial weather world, by the way, we're beginning to see AI models that are as good, or in some cases perhaps better, than the physics-based weather prediction models, because they are capturing physics that are just not tractable in the physics-based models, but they're capturing it through just examining petabytes and decades of weather data, and by the way, running 10,000 times faster than the physics-based models on the supercomputer. They're running weather models on laptops now that are doing the same job as a supercomputer-sized physics-based model. And I think we'll begin to see the same progression in heliophysics, where rather than trying to make these incredibly large, complex physics-based models that run on supercomputers take 3 hours to run, we'll be running AI models of the sun, the solar wind, the geomagnetic fields, the upper atmospheric changes, and therefore, with the speed ups you can get from AI, we'll be running ensemble models, uh, thousands of ensembles in the time it takes a large physics-based model to do a single run. And I think that's going to revolutionize the prediction, at least, of space weather effects.
It sure is an exciting time, isn't it, to be involved in heliophysics and space
Oh yeah,
weather research.
absolutely.
So, as far as resources go, of course, with Aurora specifically, but also space weather, there is the NOAA Space Weather Prediction Center. That's one good place to NOAA, NOAA, uh, to get information about this. What other resources can you recommend to people if they want to learn more about space weather and about Aurora? Perhaps even something at your space weather center.
Yeah, we have a very good data sort of portal, if you will, that collects data from all over the heliophysics world. in one convenient web-based place. It's called the Space Weather Data Portal, and you can just Google that, and it's running on the LASP server at the University of Colorado here. It's a great way to look at both solar data, solar wind data, magnetospheric data, all in one convenient website. You don't have to go to one database to get your magnetospheric data and another to get your solar data. It puts it all together in one easy to use website, and you can plot all of these various effects from the sun to the mud, if you will, very easily. You can just give it a date range and it will go and get the data for you. And it doesn't download the data, so it's not taking a long time to download data. It's really just pulling the data from the existing data sites, and there you go. So we call it there's also a Space Weather Now page on a subpage of that particular web page, which will give you minute by minute updates on these key parameters like solar X-rays. So you can watch a flare go off. It's everything they have at the Space Weather Prediction Center at NOAA, but they get it in 3 seconds. We get it every 5 minutes or so. But it is like having a professional space weather station that you can just watch things happen on.
Do you think that's in our future? Will we have weather persons on the morning news that walk around in front of their green screen and tell us everything from what our UV exposure to reliability of GPS and other technologies is for that day?
I hope so, and we have somebody like that in the field right now. If you Google space weather woman, Tamitha Skov, who's a PhD researcher from the Aerospace Corporation, has essentially a constant YouTube newscast that she keeps up with and gives these sorts of forecasts and nowcasts and talks about the impact she's been hearing. So she's actually here in Italy as well. But as you can imagine, she's been extremely busy the last couple of weeks with both keeping up her YouTube cast and also interviews. She gets a lot of interviews from people, particularly from amateur radio operators who want to know, how long is this going to last, basically, and things like that. So yeah, I think that'll come, and I think Tamitha's on the frontier of that right now.
Excellent. Hey, Tom, as always, this has been great. Thank you so much for joining us on the Wormhole today. We appreciate you going out of your way as you're traveling in Italy to join us and share some of this information. And we sure look forward to having you again here on the Wormhole.
Well, thank you so much, Jonathan. It's always great to be on here and talk with you, and enjoyed it a lot, of course.
Travel safely, my friend. We'll talk soon. And thank all of you for joining us. We hope you've enjoyed this time with Dr. Tom Berger. It's always great, of course, having him on, and we hope you'll subscribe and tune in to future episodes of The Wormhole. Thanks for joining.